Yo, hi. Related rates. So, what are related rates? Um, Simply put, related rates are a way we can apply derivatives, use our skills to kind of compare multiple rates of change at once, given a couple of constants, right? Uh, right now I have an example on the board. The most common example you'll see of a related rates problem will be probably filling up this conical tank with water. Um, so I thought it'd be useful to kind of have this example because it's kind of all-encompassing. We'll go over some tips, kind of tricks for solving these. Sometimes they can be tricky, but it's pretty step-by-step process, pretty straightforward. Taking a calculus class, this will be a small portion of it. We might get a couple problems on these, but I think it's a pretty interesting way we can use derivatives and a little bit of geometry, some algebra, to compare the way things change. So let us begin. Right. I think it's best learned through example, right? So we're gonna kind of jump right in and I'll explain things as we go. I'll try to make some clarifications. Let me know if you need anything. So normally in a problem we'll be given kind of a block of text. I've simplified it down to these 3 bullet points. We have this conical tank, which I've very artistically drawn right here. And we're filling it with water, right? At a rate of 2 centimeters cubed per second. So we're gonna have some sort of pump filling this tank with water. And now, there's cat is attacking that right there. So tricky thing here is we fill up this tank with water. Here, the kind of the volume is going to have a large impact on the height of which this tank filled up. But then up here, you have such a large radius that it's going to take a lot more water to make a change in height, right? And so what we see is that given that our rate of volume change is constant, the rate of change of height is going to vary as time progresses. It's going to vary with the radius, which is really varying with this whole time deal. So with related rates, it's kind of a more real life application of calculus, and as such, um, we're going to be using time derivatives. Time, we're not going to have discrete time values, like I'm not going to tell you to plug in time t equals 1 or 2 or 3 really ever here. However, we're going to be differentiating with respect to time, not with respect to radius r, height h, or volume v, as I have listed the other variables here, right? The reason for that is everything, all of the change in our variables here, like our change in height, change in radius, and all of that, is all a result of how the geometry of our object is changing with time. Time passing as our volume rate is static, right? Kind of towards the beginning here, I'll reiterate this in different words. At the bottom here, when our time is still low, I guess. Cat. Sorry there. Try not to interrupt. Um, Closer to the start of our trial or experiment or whatever we're doing here, to the beginning of filling up this tank, we have very, very high change in height here, but towards the end of our experiment or trial or whatever, we'll have a very, very low change in height. And there's time in between there. So when I see a related rates problem, when I recognize one, I always like to ask myself, and I'll be over here, what do I want? I'll try to write that better. What do I want? And I'll have that as like a list. And then what do I have? Okay, so what I have is that they've given us a volume rate of change. They are saying that this tank is filling up at 2 centimeters cubed per second, and that is constant, that's not changing. So we can express that as dv dt, because what this really is this is a change in volume, right? So look out for those keywords: fills, expands, all of that. dv dt is going to be equal to 2 centimeters cubed per second, right? Now, I forgot to discuss what they're asking here in this problem that I created. We are tasked to find the rate of change of height. So how is our height changing instantaneously? I should probably put instantaneous rate of change of height, because when h is equal to 3, so when height is equal to 3, might not be able to see that there. So when height is equal to 3, what is the rate of change of height? Right, and so that's probably the most common way this specific problem in related rates generally will be addressed. You'll also kind of see problems like with triangles and like something's moving away from the triangle and it's trying to find how this length of this leg is increasing, right? Or this hypotenuse, right? Or sometimes you'll see there's like a circle and that circle's expanding and it'll eventually become a bigger circle, right? And there's some other tricks you have to use for that, right? But here we're being asked when the variable is at a constant 3 centimeters, I should put that centimeters, what is the rate of change of that variable, right? And so that's what related rates is going to allow us to do this. So we want dh dt, given that, I guess you can write given that however you want, given or when h is equal to 3 centimeters, right? So when h is equal to 3, what is dh dt? And that's really all we want, and this is all we really have. So let's go through the steps. We have this volume formula. V, the volume of a cone, is equal to 1/3 pi r squared h. And all these variables match. R for this radius here, h for this height, right? Pi is our ratio of a diameter to its circumference in a circle, and 1/3 fraction, right? We're going to use this equation to find dh dt, because if you remember back to the implicit differentiation video, we can kind of differentiate both sides of this and come up with these variables that we have and want. So I'm going to rewrite this down here. If v is equal to, and I'm going to write this as pi over 3 r squared h. Okay, we want dh dt, we have dv dt, we can get those, I see, by differentiating, right? So now with implicit differentiation, remember, I said earlier, we're differentiating with respect to time. Seen here, our givens are in respect to time, but none of our variables are t. This isn't a y equals x, this isn't a y equals t. There's no time here. So we're going to have to be a little bit creative, right? We're going to kind of differentiate both sides. We're going to differentiate this volume side and differentiate this volume expression side. I'll do that down here. On the left side, it's pretty easy. We're just going to get dv dt. There's nothing special about that, no tricky derivative. That's what I like about related rates. A lot of the times the derivatives are going to be pretty easy, at least for now. Not going to have to worry about too much. So here over on this side, we're going to have to do some product rule. This pi over 3 is a constant multiple. We don't really have to worry about that. It's like if we were to differentiate 4x, we wouldn't differentiate this like a product. We don't worry about the 4. We just, do our little power rule, subtract from the power and all that. We just get 4. So here we're going to do a similar sort of thing. We're going to have pi over 3 out here in front. And then we're going to be differentiating this kind of part here, this r squared h. Now this is going to be some left, d right. It's going to be r squared times dh dt. Now we already have both these variables, but let's keep going. Plus, now right, d left. Okay, d left. We're going to have to do implicit differentiation here because we're differentiating with respect to time, not with respect to r. It's going to be times 2r. Now we have the chain rule. Remember, that's how implicit differentiation works. Times dr dt. Okay, yeah, kind of weird here. We don't have a value for r, and we don't have a value for dr dt. So what do we do here? Okay, so I have this diagram up here. I've drawn a similar triangle. Bear with me. You see this kind of a straight down height that I made and this straight across radius I've made. Now what we see is as this tank filled up, we're going to have different heights of water, but these are all going to make similar right triangles with, and I can redraw it over here to make it a bit more clear. we're going to have varying lengths, or we're going to have h here, we're going to have a larger h up here, and r here, right? Really bad visual, but bear with me. The ratio of r to h is always going to be the same because this is a similar triangle. We always share this angle here, we always share this right angle, and we always share this angle. So all three of these angles are always equal. We're going to have a similar triangle, right? What do we do with that similar triangle? Well, let's go up here to the top right. Actually, no, let's stay here at the bottom right. We have, if the tank was full, completely filled, we would have a full height of 6 centimeters, which I've written here, and a full radius of 2 centimeters. But let's say that height is equal to 3 centimeters, like they ask in the problem, right? Height is equal to 3 centimeters, well, what would radius be equal to? So, you know, we could do some kind of ratios here. R over h is going to be equal to 2 over 6, right? So r is going to be equal to 1/3 h. Or you could just realize that 2 is 1/3 of 6, so this r value must be 1, right? That helps us. So we know that r is equal to 1/3. Oh, I'm writing right on the bright spot, aren't I? I'll be back down here. We know that r is equal to 1/3 h from our similar triangles, right? Okay, and we also know that if h is equal to 3, r is equal to 1. Okay, well, we have an r value of 1, we can plug that in here. What do we do about this dr dt value? Well, if r is equal to 1/3 h, I believe that dr dt is equal to 1/3 dh dt. Did some more implicit differentiation there, derived both sides. We came up with an expression for dr dt. We can substitute that in. And so I'm going to come back up here, I'm going to erase our original volume formula. I'll write this final kind of thing in red here, right? We're going to have dv dt, which we know is 2, so let's just put 2 in there, right? And we can even label that centimeters cubed for a second. You won't need to, don't worry about it. Equals pi over 3 times. Now r we know is 1 at this instant, so that's going to be 1 squared times dh dt. And you know what, I'm just going to go ahead and erase that 1 squared, it's going to get in the way. Let's leave that as dh dt. Now plus, we know that at this instant, h is equal to 3 centimeters. Am I getting close to that bright spot for an eye? Oh, man. Okay, h is equal to 3 times 2, because r is equal to 1, times, okay, and now 1/3 dh dt. Whew, okay, that's kind of a lot. This reads 2 is equal to pi over 3 times dh dt plus 3, and this should all be in parentheses plus quantity, 3 times 2 times 1/3 times dh dt. Right, now, right away, I believe that 3 and 1/3 can cancel, and we're just left with dh dt plus 2 dh dt, which can all simplify into 3 dh dt, which cancels out nicely with pi over 3, just to get pi times dh dt. Wow. So if you didn't get that, kind of rewind and look at my algebra there. Maybe if I blocked something with my body, I apologize. But all this simplifies down. If we take this equation that I've written down below, which has been kind of swept out. If you take this equation, you sub in r is equal to 1, both here and here, and you substitute dr dt for this derivative we came up with over here. Dr dt is equal to 1/3 times dh dt, right? Because r is equal to 1/3 h. Derive both sides there with implicit differentiation with respect to time. Dr dt equal to 1/3, which constant multiple, times h, derivative of h is just 1 times chain rule dh dt, right? and we can substitute that in, get that, simplify everything. You get 2 is equal to pi times dh dt. I'm going to go ahead and erase this unit. A bit confusing. And as a final answer, and I'll kind of just erase this one last time, we get dh dt is equal to 2 divided by pi. And that's going to be in centimeters per second. Because your height is measured in centimeters, the rate of change of centimeters is going to be centimeters per second. Just like if you were driving in a car, right, your velocity in meters per second versus meters, change in meters, all that stuff, right? And so now we found dh dt when h is equal to 3 centimeters. Using similar triangles, our knowledge of geometry, we can conclude this is a similar triangle because they share 3 angles, all 3 angles. We have a volume formula. We use implicit differentiation to come up with an expression with only our known values and our wanted values. And we use a little bit more clever substitution here to get rid of those terms we don't know that are value, because we don't necessarily know how radius is changing at this instant with what we were given, but we can find it. It's always just 1/3 times the rate of change of the height. Right. So I'll step away, kind of let you look at all this for now. I might release kind of another post later about doing concentric circles example, very similar to the similar triangles example, except you're using circles, right? And I might release one about the kind of, usually it's a person walking away from a lamppost and there's a shadow. That's a pretty common one too. It's a bit tricky, but I hope you enjoyed related rates today. Not the most widely used thing in calculus, but I do think it's an interesting ability, a tool we have in our arsenal, things we can do with derivatives. I think it's really interesting. So with all that, see you later, class. Goodbye.